Hello, everyone. I want to explain what is the chondrite. Chondrite is the stony meteorites. Stony means that it's non-metallic. The stony meteorites that didn't melt or differentiate in their parent body. So their parent body usually are small to medium asteroids, and they were too small to undergo melting and planetary differentiation. They are formed by various types of small grains and thus since the earliest history of solar systems. And it is the common type of meteorites that arrive on the Earth's surface. Carbonaceous chondrite is a class of chondritic meteorites. It features high carbon content, which in form of graphite, carbonate, and other organic compounds, like the amino acids. And in these meteorites, they contain water and the minerals that have been modified by the influence of water. The minerals are only stable below 100 degrees Celsius. So the meteorites contain minerals that form in both high and low temperature environments and then collect together. This is the figure. And the y-axis is the relative abundance in the sun. The y-axis here. They use the spectral method of chemical analysis to calculate the relative abundance. And the astronomers use the silicon as the reference element. It means that the relative abundance in the sun is to calculate the ratio of the element and the reference element to decide the relative abundance. In this figure, we can know the composition of carbonaceous chondrite is similar to the sun, and they're almost the same. It means that we can use the carbonaceous chondrite to be the chemically unbiased sample of both solar system matter, except the volatile, like the hydrogen, carbon, oxygen inner gas. You can see the figure.
I have a question, but it's more like a question that I asked myself. I don't understand the real importance of carbonaceous chondrites. We can another proof of what's made of the sun, but I don't understand really why is it so important when it is presented.
Axel asked, what is so important regarding carbonaceous chondrite? Do you have an answer for that?
I think that is maybe because the carbonaceous chondrite his composition is similar to the sun, so that on the Earth we can know what is on the outer space. So we can use the carbonaceous chondrite to know that the other meteorites arrive the surface, and we can know the composition to know that what is.
I think Chloe gave a very good answer. That's something we know after we analyze the composition of carbonaceous chondrite. We realize that its relative abundance is very similar to the sun. These two materials, the sun and the carbonaceous chondrite, they share the greatest similarity in composition compared to other meteorites. The good thing of that is if we do some dating for the carbonaceous chondrite, it will show us the age of the solar system. That's the reason we think carbonaceous chondrite is important. What does it mean by differentiate? Here, Chloe wrote, meteorites that didn't melt or differentiate. What does that mean?
I think the differentiate here means 可能被破坏过之类的吧。陨石来到地球被我不太确定。
Perry mentioned maybe it's not differentiated by the atmosphere when the meteorite fall onto the Earth. Does anyone have an answer for that? What does it mean by planetary differentiation?
No.
It might be when something melts and because of the gravity, some elements are going to separate in different layers. Like on Earth, we have our iron core. The lighter it is, the more near to the surface it's going to be.
Very good. That's one of the process. That's something we will talk about maybe in 4 or 5 weeks. The differentiation of core, mantle, and crust. Why do we have 3 layers? Because they are differentiated. But for chondrites, they don't. How do they know that? They are not the product of differentiated planetary material. We will talk about this later. Okay. I think previous students hate this topic a lot because later on, at some point, I will start to talk about the motion of the planets, the orbit, etc. And it's like, oh, I don't want to know that. I try to minimize that part. So we want to continue from where we have been. We have talked about hydrogen and helium formation right after the Big Bang. We also have talked about heavier element formation, heavier than beryllium. How were they formed? They were either formed in stars by nuclear fusion or S process, or they are formed by supernovas. Where are we going? So far, we have only talked about nuclei. Are you made of nuclei? Are you made of single atoms? Like when we have a piece of gold, I would say, yes, it's made of gold element. But will you say you are made of elemental carbon? Of course not. You are made of carbohydrate, lipid, protein. These are in molecular form. So how does planetary system like the solar system form? Because in planetary system, we see more complicated chemical form. Basically, we see molecules. But so far in nuclear synthesis, we have not talked about molecules. Where could molecules form? That's our question for planetary systems. So we need to first talk about environments for molecule formation. This is from the chapter that I did not ask you to read. If you want to know more, you can read the chapter 4 of our textbook. Again, we need to compare stars with other environments in the universe. Stars have super high temperature. You already know that. It's a place where we have nuclear reactions. And the state of matter is plasma. Plasma is the so-called the fourth state of matter. What is state of matter?
Solid, liquid, or gas.
Very good. So that's you know from your school education, right? You know we have solid, liquid, gas. It's dependent on what?
Temperature and pressure.
Yes, that's the three states of matter that you know. But now I'm telling you there's a fourth state called plasma. You barely touch this state because it requires a very special condition. What is that? Look at this. In this figure, this is the three states. They are present at relatively low temperature and high pressure. Where can we find plasma? High temperature and relatively low pressure. These are the phenomena we know. Have you worked with it? Partly. Look at this. Flame is a plasma. That's probably the major plasma you ever seen or work with. And what are the other plasma that this course already addressed? Solar core or nebula we are going to talk about. These are all in the form of plasma. So plasma is closer to what? It's closer to gas. So more about plasma. Plasma is ionized gases where the elements are stripped of their electrons. It's a chaotic mixture of ionized nuclei and electron. The most common state of matter in the universe, but it's rarely seen on Earth. It's observable on Earth through the solar aurora, the northern lights, neon, flames. There is an instrument called inductively coupled plasma mass spectrometry, in short, ICP-MS. It's a very popular instrument for trace metal analysis. In our department, we also have another instrument called ICP-OES. When you see the term P, it means plasma. That means this instrument adopts specific kind of technique that convert the compounds into plasma for measurement. It's not measuring molecules, it's not measuring ions, it's measuring plasma. So that's the state of matter in stars. Apparently, we need some place which is not so hot and denser for us to exist, right? Where can we find regions with lower temperature and denser materials in the universe? The answer is nebula. We also call it interstellar cloud. I don't know if any of you are backyard sky watcher or any of you join any club for sky watching. When I was a high school student, I was in such club. Our favorite targets are usually nebula because they are very beautiful. This place has lower temperature, usually less than 1000 K. This is a place where you can really find chemical reaction, not this place. Here we have the state of matter that we know: solid, liquids, gases. These slides explain types of nebula, but I will just show you some beautiful figures. That's the reason we like to watch nebula, because they are much more colorful. This one is Orion Nebula. It's a diffuse emission nebula. The clouds here, they are diffusive. So within the nebulas, there are some stars. And the stars emit some UV radiation to lighten the cloud here. Otherwise, you shouldn't be able to see this cloud. Eagle Nebula. This is from the Hubble telescope. It is the most well-known nebula, pillars of creation. It's again a diffuse emission nebula. You see the distant star here, and the star is irradiating the clouds here. So you see them. You see that this is really dense. Ghost Nebula. It is a diffuse reflection nebula. There's no real nearby stars that irradiate. So it just reflects the starlight from other more distant stars. And Horsehead Nebula. You see it's a dark nebula. You might think there's nothing here. On the contrary, there is a lot of stuff here. And because the material is so dense, it totally obscures the starlight behind. So you feel that it's a shade, but it's actually dense material here. So these beautiful nebulas pictures are all from Hubble telescope. From Earth, using some telescope, you can see only very vague picture, but still when you see it, it's like, wow, I win the prize. So that's the delightness that nebula will give you for backyard sky watcher. After nucleosynthesis, there must be a place in the universe where these nuclei or atoms, they can slow down and interact with each other to form larger molecules. There have to be a place like that. Where is that? In nebula. How do we know that? We need to be able to measure the chemical composition of nebula. How do astronomers analyze the chemical composition of cold objects? Stars are very hot, so you can use the visible light telescopy. However, nebula, they are much colder. How do you analyze its chemical composition? If any of you watch the video, you will see this. Radio telescope. This is using the spectrum of radio wave, not optical telescope. Optical telescope is only for stars. It operates in the radio frequency portion of the electromagnetic spectrum. Let's review the spectrum. Previously, we were focusing here, visible light. But now we want to see colder material. We need to use this, radio waves. It has much longer wave and lower energy. Molecules will emit specific electromagnetic fingerprints. If you watch the video, you will see that astronomers, they were looking for the presence of water and the presence of molecular oxygen in the universe. And then they realized that actually in the universe, water is everywhere. However, molecular oxygen, that means O2, is absent. It's very difficult to find O2. On our Earth, we have molecular oxygen, which is actually very strange. Because for the universe, it's difficult to find molecular oxygen. This is detection of water in a remote galaxy by radio telescopy. That's back to 2008. That's probably by the project presented in the video. This is the spectra of the telescopy. You see a peak here, and the peak corresponds to water. So that's how they identify the presence of water. Using radio telescope, astronomers could identify the chemical composition of nebula. They figure out that interstellar clouds are consistently mostly of ice, but they also contain dust, oxides, and metals. You see more advanced form of matter. Here, the ice, do not think of it as ice cube for your drinks. It's actually frozen volatiles. That could mean any kind of gas, like a nitrogen can be volatile, oxygen, methane, CO2, they are all volatiles. That means most of the existing interstellar clouds are made of materials ejected during stellar evolution. They are not from the virgin interstellar cloud after the Big Bang. Because you see this more advanced form of matter. You have metal, so there must be iron, and you have oxide, that means you have maybe silica, you have magnesium, calcium. If you have these elements, these materials were the remnants of stellar evolution. In interstellar clouds, there are some unusual conditions. The first thing is stellar wind. Actually, today we also have stellar wind. Our stellar wind is solar wind. Every day, the Earth is being blown by the solar wind. The stellar wind or the solar wind is the star is emitting its plasma outward to its surrounding. Plasma is charged. The proton and electron in the upper atmosphere of stars get accelerated by the high temperature. So this explains the formation mechanism of stellar wind. Because the particles in the upper atmosphere of the star is accelerated, at some point they will reach the escape velocity, and they will simply run away from the star. The mass loss in the form of stellar wind is negligible compared to the total mass of the star, but bombardment of the high-energy particles onto interstellar material is important for formation or breakage of molecules. These particles emitted in the stellar wind, they will interact with the nebula material and create new molecules or break old molecules. Today, in Europe, there are places where we can see the interaction of solar wind with the Earth's atmosphere. That's in Northern Europe, where you see the northern light. You see this beautiful light in the sky in Northern Hemisphere is actually caused by stellar wind. The second thing is not particles. The second thing is UV radiation. The stars have very high temperature. The wavelength of black body radiation. I think this concept has been mentioned in your chemistry course, so I will skip it now. The wavelength of black body radiation decreases with increasing temperature. That means in this direction, it has shorter wavelength. If a black body has higher temperature, the wave it emitted will be in this direction, shorter wavelength, higher energy. Strong UV radiation can ionize chemical species and break them apart. I think none of you have worked with UV radiation. 3 years ago, when the COVID just started, at that time, the mask is not enough for the whole population. Therefore, someone would say, how do we reuse the mask? Because in my lab, one of my previous students works with UV light. And we know that UV light has the effect of sterilization. Therefore, one day I took my mask, used mask, to my lab and leave it under my UV light for maybe 1 hour. What happened? But when you take it out, it has a horrible smell, very, very horrible smell. That is not possible to use it anymore. Today, it's possible to buy just UV light. It's a little bit like the lamp. And you leave it here, what will happen? After 1 hour. All of us, we need to leave the room. Why? Because the oxygen here will turn into ozone. So it's very powerful. Usually for people who work with trace metal, they will use UV light to decompose organic matter. UV light also has the power to decompose organic matter. Summary. Interstellar clouds are the largest factory for molecules. That's where molecules are produced. Both organic and inorganic compounds are formed. And then, these molecules are the raw material for planetary systems. That's our topic today, the solar system. Now I'm going to play this video. There are several unusual characteristics of the solar system if you compare it to a system with 10 randomly moving balls. The most unusual characteristic is there is orbital movement. But we are so used to it that we no longer think it's a surprise. The orbits, they are not true circles. All planets lie close to the plane of the ecliptic. All planets rotate in the same direction around the sun. They are all counterclockwise. The planets closer to the sun has shorter orbital period. The planets at more distant place of the sun will move like this, slowly, and closer will be like this. And the orbits of planets are regularly spaced. Okay, this is a mystery to me. I don't know why. If you read the textbook, it will tell you this is the so-called Bode's law. The distance between orbits of successive planets increased by a factor of 1.7. This is the planet order. They do seem regularly spaced, except for here, the asteroid belt. That's the reason people believe that asteroid belts represent a failed planet. Planets, they are accreted by smaller material. But asteroid belts are failed planets because these material, they did not accrete together to form a larger planet. I was quite curious about the reason for the Bode's law, so I actually Googled it. There are some scientific journals say, we no longer accept articles discussing the underlying mechanism of Bode's law. So I don't know what caused this. The planet size. The planets closer to the sun are smaller. That's us. The planets at a more distant place from the sun are larger. You see the big difference? All planets are small compared to the sun. So is that coincidence or is there a reason? What you guys learn from your school education is the Kant-Laplace model. It's proposed in the 18th century. This clear organization of the solar system gave rise to the nebula hypothesis by these two scientists. They suggested that the planets and the sun, they are formed from a single spinning flat cloud, which means they are from the same nebula. The nebula spin and spin and spin. At the end, it becomes the solar system we know today. And the spin of the planets and the existence of the ecliptic conform to means agree or support the original plan and the spin of the cloud. These two evidence, the spinning and the existence of ecliptic, are supporting evidence for the hypothesis. We have talked about the first part, the behavior of orbital and rotational movement. Now we talk about planetary density. So we know density is calculated by mass divided by volume. Kepler, he figured out how to measure the density of planets. The mass of a planet can be determined from the gravitational influence that planet exerts on the orbits of its moons or neighboring planets. The planet has a gravitational field. It will affect the moon, that means its satellite, or the nearby planets. Based on that, he came up with this mathematical expression. MP is the mass of the host planet, in this case, our Earth. R is the distance at which the moon orbits the planet. The Earth-Moon distance is R. V is velocity of the moon around the planet. And G is the constant of gravitation. So using that, he can estimate the mass. The planets, we can see them. I mean, in solar system, we can see them. So it's relatively easy to estimate their volume. That's the mass distribution. We have two giants, Jupiter and Saturn. These are their density. As large as Saturn, if you put it on water, it will float on water because its density is less than 1. For us, with small inner solar system planets, we are small but compact. We have density higher than 3. And for the outer planets, they are all small in terms of density. Implication. The outer planets are consisted of something lighter, and the inner planets are made of something denser. That's what you will read from the density value. Normally, elements in the upper rows of the periodic table have lower density than those at the bottom rows. Interstellar ingredients, that is ice, oxides, and metals, they all have distinct densities. So now you can guess the outer and inner, which one will have more ice? Outer, of course, because this is the source of the low density. Here I give you a table regarding the commonly seen planetary material, their density and their melting point. Those with low density will have low melting point, and those with high density will have high melting point. These gradients correspond to the gradients in the solar system. This is the inner planets which have denser, high melter. Those at the outer planets have lighter, low melter. So far, this is our guess. From Kepler's law, we only know bulk density. If you think of something with a density of 1, it could be something made of purely water or something that is the combination of some very heavy material and some very light material. So we don't really know what is the composition here. We need some solid proof to know, okay, this is indeed metal, oxide, or ice. We need evidence. Planetary composition. Of course, we have some evidence from the Earth. The density of Earth's surface is 2.7 to 3.0 gram per cubic centimeter. If any of you will work on sediment in the future, this is a number you should remember, 2.7. Because when you calculate the volume of sediment, you need to hypothesize its density. And the density we usually use is this value, 2.7. But the average density of Earth is 5.5. Here, this is the Earth's bulk density, 5.5. Where are the dense material?
在地核那边吗？
Very good, in the core. But do we really have any physical material from the core? No. We never have any physical evidence from the core. It's impossible to sample the core. How do you know the core is made of metal? Because the textbook says so, huh? That's the reason we want to study meteorite. They are pieces of debris from sources as asteroids or comets that survive its impact with the Earth's surface. Axel asked why it is important to study carbonaceous chondrite. There is an even more fundamental question. Why do we want to study meteorite? Actually, those who study meteorites or chondrites, they are mostly geologists, not astronomers. Here in Taiwan, very few people study this. But in US or Australia, there are a group of scientists, basically geoscientists, who study meteorites, chondrites. Why? Because they are considered broken planets. It's impossible to break our own Earth, right? You can't even sample it. If our neighbor, it has some failed planets and the failed planets fall into the Earth, you can say, hey, let me take a look how you are made of. Then I will know how I am made of. That's the reason why we want to study meteorites. And crucial characteristic of meteorites, in 2 weeks, we will talk about dating technique. Meteorites will be the first material we will talk about because it will tell you how old the Earth is or how old the solar system is. Direct age measurements show that most meteorites are as old as the Earth or as old as the solar system. That would be the more correct conclusion. Many meteorites have unusual texture, which can only be formed outside planetary environments. What does that mean? I will tell you later. Most meteorites are solids from the solar nebula. They have not been accreted into planets. I mean, they have not been accreted into the 9 major planets that we know. They might have been accreted into smaller objects, but later, maybe by some bombardment, it's broken, and then its debris fell into the Earth. So what does it mean by unusual texture? This. The name of this texture is called chondrules. In Chinese, it's called, you see, that's the mineral grams. Can you see any mineral grams on Earth with this appearance? Round-shaped? Probably not, right? Because the mineral gram you see is always with an angle. You will not see a round-shaped mineral gram. So this unusual feature is called chondrule. And meteorites with chondrules, they are called chondrites. In Chinese, they are called, okay, it sounds very similar, but they mean different things. And this is how chondrules looks like under cross-polarized light microscopy. So under a very special type of microscopy, you see they are very beautiful, a little bit like mosaic. Formation of chondrites. Chondrites have chondrule texture. Chondrules were once molten rock droplets which condense in the very low pressure of space. On Earth, because we have at least atmospheric pressure, underground we have even higher pressure, so there's no way for us to have chondrule in our rock because we have enough pressure. But in space, it's possible to have chondrules. Therefore, it is believed that chondrule represent pristine materials from the solar nebula. Ordinary chondrites represent 82% of total finds on Earth. They are mostly rocks, silicates with very low iron and carbon contents. They are mainly made of high temperature mineral. How high? Higher than 1,100 degrees Celsius. Carbonaceous chondrites means chondrites with chondrule, but it has more carbon content. It represents only 4% of total finds. It has organic carbon and water, and it contains both high temperature and low temperature. That's what Chloe presented, lower than 100 degree mineral phase. This is the volatile odor of different elements. With higher odor, you see nitrogen, hydrogen, carbon. They are very volatile. This is the volatility coefficient. This means the content in ordinary chondrite versus the content in carbonaceous chondrite. This figure shows you how depleted ordinary chondrite is in terms of volatile content compared to carbonaceous chondrite. However, since this volatile material can be found in carbonaceous chondrite, this material should have been there in the solar nebula. But it's gone in the ordinary chondrite. There must be some reason for that. Previously, I talked about chondrite. There is another type of meteorite called achondrite. It represents 8% of total find. So you know in English, if you have A in front of a noun, it usually means the inverse or the reverse of that term. Achondrite do not have chondrules. It may have chemical composition comparable to chondrite, but have texture similar to igneous rock like this one. Look at this. I think by looking at this figure, you will say, I think this is a piece of igneous rock on Earth. But in reality, it is achondrite. So your next question would be, how do you know it's meteorite? Chondrules, it is the most direct evidence and the most visible evidence. But in reality, chondrites or meteorites usually have very specific chemical signature, especially isotope. But this requires further chemical analysis. And chondrule is something you can see with your bare eyes. In this case, it's no longer possible to say it's a meteorite based on your bare eyes. This is based on chemical analysis. This kind of achondrite, you see, it has these mineralograms. If we do some microscopic observation, you will not see these round mineralograms. You will see these grains with angles. They are formed in the interior of larger meteorite parent bodies and undergo melting and recrystallization. So you start to see crystals. That tells you what? If the meteorite is large enough, there can be igneous cycle. So igneous process is related to the size of that planetary objects. Smaller object cannot afford igneous process because you are too small. This looks like what happened on Earth, right? In surface Earth, we can observe this. And lastly, we have so-called iron meteorite. In this case, we no longer call them chondrite or achondrite. We call them meteorite because they are simply a piece of metal. It's 5% of total finds. Iron meteorites consist overwhelmingly of an iron-nickel alloy. They form the Wittmann-Stitten pattern. This. Otherwise, you might think, Why isn't this produced on Earth? But when you slice it open, you will see this kind of pattern. This pattern, based on some experiment, can only be formed in the core of a larger meteorite parent bodies where the metal core is well insulated and cool down very slowly. Then you will have this pattern. If you are a very small planetary object, you only have chondrite. If you are a little bit larger, you might have some igneous process, then you can have achondrite. If you are even larger, I don't know how large it has to be, you can have an iron core. Based on these evidence, geoscientists think this is also how it works on the Earth. And because the Earth is large enough, we will have an iron core, we will have a silicate mantle, and then we have crust. This figure is the assignment. I will skip this one. So what we learn from meteorite? Variation in meteorite composition is mainly controlled by the relative abundance of iron, magnesium, silicon, and oxygen, and the content of volatile compounds. Denser meteorites will be mainly metallic iron. In the middle, we have silicate plus iron oxide. Lighter meteorite will have silicate plus iron oxide plus volatile compounds. And they are in different density. So variation in planetary density can then be explained by such compositional variation or combination. That's how scientists figure out what might be the chemical composition of the planets. So far, I have been telling you it's difficult to get real physical sample from the Earth, from the core, and it's difficult to get physical sample from other planets. The only physical sample we have is probably from the moon. But a few years ago, there's a very famous project called Cassini. So let's first enjoy this video. That was 2017. I was at home watching the broadcast that NASA sent Cassini into Saturn. It's a very moving moment for us. You might wonder, what did Cassini really figure out? So let's look at some results from Titan. Let's talk about the final part of today's lecture, scenario for solar system creation. This is what scientists believe how the solar system was created. At the beginning, there was so-called presolar nebula. Presolar nebula, they are materials ejected from earlier generations of massive stars. There are different forces acting on these presolar nebula. The gravitational force attempts to collapse the cloud, while the gas pressure attempts to expand the cloud. Because we know that presolar nebula, they are material ejected from earlier generations of stars, that explains why the sun and some chondrites, they have similar chemical composition and they have heavier elements. They have age of 4.6 billion years old. Then, at some point, the nebula will start to spin. This is the top view of the nebula. It will start to spin, and the clouds spin more rapidly as it collapses because of conservation of angular momentum. So that means the more it collapses, the faster it spins. This is because of the conservation of angular momentum. So what is conservation of angular momentum? So look at this girl. She is spinning. If she holds back her arm, she will spin faster. If she extends her arm, she will spin slower. That is the so-called conservation of angular momentum. This also explains why the inner planets spin or orbit around the sun faster than the outer planets, and all planets spin around the sun in the same direction. Then the third stage is the formation of the proto-sun and protoplanetary disk. This is the side view of the presolar nebula. As it starts to spin at some point, it will start to flatten, and then it will develop the protoplanetary disk. Spinning will cause the cloud to flatten out. This is pretty much like the production of a pizza dough. So the pizza dough was originally a round dough, and the more you spin and spin, then it will flatten out and expand.
Look at that.
So look at this. Much like forming a flat pizza out of dough, and it will take the form of a disk. That explains why the solar system has the plan of the ecliptic. The fourth stage is accretion of protoplanets. This is the side view of the protoplanetary disk. Protoplanets start to develop. This is the top view. Accretion of materials in the protoplanetary disk starts, forming protoplanets. The temperature gradient in the disk causes very planetary composition. Because the closer the material is to the sun, the higher the temperature will be, so the low boiler or low melter will evaporate and be expelled to the outer solar system. And at the same time, material while orbiting around the sun will start to accrete to form larger material or larger protoplanets. Why do outer planets have larger mass? Because the low melter, such as ice, is expelled to the outer planets, and where the temperature there is low enough, this volatile material will solidify and then accrete on the protoplanets. At some point, the young sun clears the interplanetary space. Today, in our solar system, in the orbit of the planets, there are not so much other smaller objects. This is because the young sun has helped to clear the interplanetary space. The young sun emanates strong solar winds, which blows away most gases and dust that are not accreted into protoplanets. Therefore, we know collision is not a frequent event in today's solar system, but was frequent in the young solar system. We will talk about this when we talk about the moon. And the solar winds also cause the spinning of the sun to slow down. Summary: formation of planetary system is a natural process that follows the formation of interstellar clouds, nebula. This appears to take place throughout the universe. Therefore, whenever you see a star, it's very likely that it is accompanied by other planets. This is confirmed by a report published in January 2013, where astronomers at the Harvard-Smithsonian Center for Astrophysics reported that at least 17 billion Earth-sized extrasolar planets with orbital periods of 85 days or less are estimated to reside in the Milky Way galaxy. That means our own galaxy. And for the whole universe, there may be more. Next week, we will talk about mineral chemistry. For A group, please explain the followings: Aufbau principle, Pauli exclusion principle, Hund's rule, fill out the orbital configuration for elements in the table. Next slide. Octet rule, and draw the octet of CO2. So these are all general chemistry content. I think you still remember this. This is not in the textbook. In the reading material, the B student will find answer for this question. Explain the following concepts: Pauli's rule 1, Pauli's rule 2, coordination number, and isodesmic, anisodesmic, and mesodesmic.